Okay, let's take a look at the software tutorial. How much time did I give you two guys on this? It's a little bit more than a week, right? Still the Tuesday after next week. Have you taken computer architecture yet?
No,
not yet. All right. So have you programmed assembly yet?
No.
Okay. So it's a bit different compared to C++. It's very bottom level programming language and directly dealing with registers. The registers can be used for storing data or instructions. So instructions are just assembly instruction, can be whatever being stored in the register, it will eventually be 1 and 0s, right? Mm-hmm. You know how that works? For example, you program in either Python or C++, it's being compiled into machine code and eventually being stored in the instruction memory. And then there's a, if you look at here, or sometimes it's called program memory, and there's a program counter, so it counts to the next one. So it's going to take out that instruction being stored in here and send it to the, some of the intermediate logic blocks and eventually arrives ALU. So these instructions are just 1 zeros. If this is an 8-bit computer, so all the instructions are going to be 8 bits. It's just 1 zeros. So you remember when you program in the interrupt part of the what's that tutorial? LCD, right? So the interrupt with the Arduinos. So you have to write into the registers, remember? So you got a register and you have to toggle this pin in order to turn on a specific function of the register. So it's actually all the 1 and zeros. It's kind of very abstract because you don't know what's going on for the hardware. It sometimes can be a pain. But the good thing is you don't have to worry about the hardware. Just turn it on, it's going to be on, right? Or you turn on that function. It's very similar here. But the good thing is you don't have to program in machine code, which is 1 and zeros. Okay, you can imagine that. You couldn't remember, like for example, one instruction like add or and, right? You want to add, or for example, and the numbers in these two registers, okay? And the AND is the operator, and that operator has a specific 8-bit machine code. So you probably just prefer type of AND instead of 8 binary numbers for that instruction. So the assembly code is already very close to the very bottom level, which is the machine code, but still need to be compiled because the computer only understands 1 and zeros, or the digital circuits only understand 1 and zeros. So the assembly code will be compiled and converted into machine code, which will be stored into the memory, program memory here, right, or the instructions as the 1 and zeros. Okay. This is the core, or it's a CPU we're going to use, and it's a soft core, which means it's not already fabricated into the FPGA because this is a Verilog thing, and you synthesize it, and it's going to be converted into a hardware or physical circuit into your FPGA. So some of the FPGA board we have in the lab, they have a hot core. You can look at the top of on the top of the surface of the box. It says it's ARM Cortex 7, Cortex like 10 or something. These are all the names of versions of the ARM cores. And if you see an FPGA board has a Cortex something core in it, claimed in it, which means it has a hard core already being fabricated in the FPGA. But it can still program the FPGA using Verilog because they also have all these other lookup tables for you guys to program and synthesize. So you can make the connections and design peripherals for that CPU. So for example, you want to write an SPI or I2C port. It's a digital block, and you can do it in Verilog and synthesize it and make it into an IP block with all the pins, and eventually make the connection in your Verilog. to the core. And Xilinx have the Vivado IDE you are using. You have used the IP core, the ROM IP core already, right? Have you? Yeah. So there are multiple different IPs, can be memory cores, can be CPU cores. So this core's name is called Pico Blaze. Pico Blaze. It's a very simple 8-bit CPU that we can use. And there are many other CPUs available on the market, can be open source. For example, RISC-V is a 32-bit CPU, which is gaining a lot of momentum most recently. Hopefully we'll probably replace ARM in 20 years, who knows. It's getting more attention from the society, so more people are joining the team and trying to adding more features to it. And that is open source as well. So maybe in 10 years, you buy a Samsung phone, it's going to be a RISC-V core in it. And that phone will be maybe 30% cheaper than whatever you are having right now, because the core itself costs a lot of money. They have to pay a certain IP fee for ARM for every single phone. Okay, but RISC-V is free, like Android. Right? So this is definitely not even close to RISC-V. This is a very simple 8-bit core, just for educational purpose. You can still do a lot of things. Okay, if you put the core into the IPGA and you add some peripherals and ports or something to it, and eventually you got an ASIC, and your ASIC or the IPGA on your Basys 3 board is basically a what? If you have a CPU in it, and you can put instruction in it, basically your IPGA, your Basys 3 board is what? Is the little CPU on your Basys 3 board becomes a what? Yeah, it's a microcontroller. Is that amazing? You can make a controller yourself from scratch. It's actually from nothing. It's just an empty IPGA board. You put a core in there, you put memory in there, you put instruction in there. It becomes a microcontroller. So what you can do with a microcontroller? A lot of things, but what's a very typical application? So if you get a microcontroller, right? What's the first experiment you put on the breadboard? Blinking LED, right? Then you can do it with your microcontroller. You can blink LED. You can make a running LED. You can even display things to the 7-segment display, even to the LCD. A lot of things. And if you put an I2C core in it, we don't cover I2C here, but we do cover SPI. Have you used SPI by far? And but you use the I2C for the oximeter, right?
Yeah.
It's just it's a wire something, wire.h. But SPI, I think we will have the chance to do it with the very last project in microcontrollers. Because usually the IC cards has a SPI interface. It's easier than I2C. Has 4 pins on it, so it's a digital hardware block in the microcontrollers or digital systems. And the SPI itself, can see it's like leader follower, right? It's very similar to UART. Has TX and RX. It's just serial communication, but they have different logic you have to follow. And so if you can write up a digital module or digital design for SPI, and you can put it into the top module as one of the modules for the top, along with the core. So which means you can put a core in it. It's going to be the CPU of the microcontroller, and you put an SPI in it. Then you can have the pins similar to UART, like RSTX, right? Your microcontroller will have SPI port, and if you put a UART in it, it becomes a microcontroller with a UART in it. Okay, so it's not just a microcontroller with all the digital GPIOs, the general purpose IOs, but also some more advanced serial communication ports that it can directly use. It's just adding more features to it. Okay, that's why when you open up the data sheet for the microcontroller, it's telling you that this microcontroller has I2C, SPI, ADCs, and PLLs, and all the kind of features, trying to make it looks good, right? Or it's more versatile because the customers need it. When you are dealing with the microcontrollers, you hope the microcontroller has SPS, has I2Cs. That's the Arduino Uno. But if you need a 2 SPIs or more UART ports, the Uno couldn't even do it. You have to do the Arduino Mega, which has more pins on it, and they have RTX1, you have TX1, RX1, TX2, RX2. They have 2 UART modules in it. You can add like I think our Arctic 7 FPGA chip has a lot of pins compared to the Arduino Uno chip you have used. You plug in, you took out the Arduino chip, and you put on the breadboard, so you know how many pins it has, right? Not too many, like 28 pins. That's why it's called ATmega 328. It's 28 pins. But I think our Arctic 7 probably has like over 40 or 50 pins on the chip. So you can actually make a very advanced microcontroller compared to the Arduino Uno one. Okay, and you can customize it. You can put 2 UART in there, right? Doable. When you do it, you just UART1, so UUT, right? And UART2, UUT2, whatever. And you can put whatever you want, based on the applications. Okay, now let's take a look at the structure. So again, we are not designing the circuit, right? The IPGA, the Verilog, or the core we are going to use already includes everything in here. So what you're expecting for this learning experience? What's the outcome here? Are we practicing Verilog? Not really. Yeah, we just need to know how to use it. So actually, you put this one, it's like an instance, right? You claim it in your Verilog in the top module as a core, and you rename it as whatever, core 1, core 2. And then you make the connection with the top modules, switches, LEDs, right? Second displays. So the output or input of the CPU will be connected to these utilities on your FPGA board. So you can use input to send signals to it, and output to verify your output. Okay, that's what we have, which is switches, LEDs, 7-second displays, push buttons on the FPGA can be inputs, and outputs you can short it. Oh no, sorry, 7-second output, right? LED, 7-second display are outputs. So the outputs of the CPU can be connected to these things to visualize the results. So we are not trying to change the details of the CPU. We don't want to do that. So just put in your Verilog, in your top module, and synthesize it, hopefully no errors. And so the main part of this tutorial is assembly, practice assembly. So you guys will program with assembly and put into the ROM. It's very interesting. So this can be a very new thing to us. A little bit attention here. So how to program it? You're expecting using Arduino IDE and through USB to program it? No, it doesn't have the feature. You should appreciate Arduino can directly push button and upload everything to it. It has a monitor in it. This one doesn't have it. So how to program it? It's amazing. So when I was in college, I have been always wondering how the computers are programmed. It's amazing. Like you type English, like C language, it's English, right? In the computer, you type it, and it's going to be burned into hardware and run it in there. It's amazing. But now you get to know how it works. You have to take this computer engineering degree and the program and get into assembly and get into the FPGAs until the senior year of the computer engineering degree. You get to understand what's actually going on the chip. It's amazing, right? It's amazing learning experience. So after getting this degree, you will be like, whenever you see a computer, you see anything, you understand the bottom level functioning, like functionality, how it works. It's amazing. So after VGA, you understand how this works, right? Yeah. When I was a kid, I was always wondering, like someone's standing behind the TV and playing the shows, but now we know it's sending pixels. Still, if you ask these other adults who haven't been in this, even the engineering people who haven't learned, who haven't played with FPGAs, they still don't know how it works. So this is good. This is good. So how to program it? Let's come back to this topic. How to program it? Like I said, you have a program memory, but the Arduino has a bootloader. Will make the communication, will bridge the computer and Arduino, the program memory of the Arduino chip. So it makes the communication and convert it into the something like machine code and put it into the memory. Okay, that thing does the job for you, or the IDE maybe convert it, compile it, convert it into machine code and send it over. Because the USB cable is also a digital cable, only it couldn't send the English, right? It sends 1 and 0s. So it must have been converted into 1 and 0s already in our Arduino IDE. So all the C language already being converted into machine code and 1 and 0s and being sent to Arduino and being saved in the program memory in Arduino. Okay, like line by line. Each line is something. Okay, so it can be an operator, can be a instruction, can be a data, right? Because the program, all the instructions are, all the programs are doing nothing but adding, multiplying, dividing, right? It's a computer. It's doing all these instructions to do things. For example, the moving the locations on the monitor for the VGA, assigning different pixels to different locations. They have to adding the address to it to move to the next location. It's always just computation. And the Arduino already has a monitor to do it. It's more advanced, so computer engineers did that job for us. Here, we don't have that. How to program it? First, are we programming with 1 and 0s? No way, right? Are we programming with C?
Yeah. Wait,
no. We don't have the compiler to do it. We maybe there will be some tools you can do it, but not here. Okay. So for embedded system engineers in the industry, dealing with FPGAs and putting ARM cores in it, sometimes they have to program and verify the design with assembly. Just expect that if you go to the industry. So you have to learn assembly. But when I was in college, I'm pretty sure for most of the college students in the country still, in their microprocessor class or microcontroller class, they still learn assembly. It's okay. I mean, I don't want to say, hey, you're doing the wrong thing, even though for one of the candidates coming, and he's a very good professor already, and he teaches microcontrollers with assembly with an evaluation board. There's nothing wrong with it. But when I was in college, I didn't enjoy that kind of style of teaching. So whenever you guys are having lunch with him, just make sure you guys don't like, hey, it's okay, it's okay. So it's been very successful for many people. If they are getting good ratings, they're teaching really well, students like it. Why do you have to say it's wrong? It's nothing wrong with it. So for example, if I teach my controller, just giving you guys all the evaluation boards, okay, so already have all the LEDs like the Basys board. I have the switches, LEDs, sensors already soldered on the FPGA, and so from the very beginning of the semester to the end of the semester, you do nothing about getting into the schematic of the board, but just programming that board with assembly, right? Trying to modify the program to blink different LEDs to show different numbers. But assembly is very difficult to communicate with any I2C devices because you have to write the drivers. Instead of in C, you can directly put a top on the top, just wire, which is the function for I2C, or any other function packages, just one line, done. But in assembly, you have to write the driver by yourself. You have to deal with all the on and off, all the timing by yourself in order to get it done. It takes probably 4 weeks to get just one function done. And so you won't be able to get a chance to work with any of the really more than interfaces or sensors at all. So the whole semester will be just dealing with assembly and the evaluation board. You don't even know like what are the devices required to drive that microcontroller on the board, because you never get a chance to solder, design and solder the power modules, right? You never know what's the voltage regulator, and you don't even know like the microcontroller just need an oscillator, a crystal, and a power supply to make it work. It's still like a mystery hiding behind the scenes, just don't know what's going on. You know, pros and cons, I think. But I do believe that you guys need to get experience of programming with assembly. So now we get a chance. And also in computer architecture, it's just the whole semester just about assembly. So it's okay, I think. I don't want to just get you guys freak out in the first microcontroller class, just since I almost dropped out from EE major, you know, or lost the entire interest in dealing with microcontrollers just by coding assembly for the microcontroller class in college. Yeah, 50% of the students in the class, 50% of the students in the class hated and got nothing out of it, just programming assembly. It was super frustrating. It's not making sense. Like, why do we have to do it? But when you get an oximeter, you know why you have to do it. I'm designing a real world product. That's how it works.
Yeah.
So now let's get into it. And these are the features of the core. But keep in mind, so I'm recording this. So keep in mind, you will see KCP SM3, which is the earlier version of the Pico Blaze core. When you are searching for, you will Google a lot, I'm pretty sure. But for example, this textbook is a really good one. It's one of the classic textbooks for IPGA coding in the country or in the world right now. But the author didn't update the core being used for the textbook, unfortunately. It's updating super quickly. So he used this one for the whole textbook. But when you programming it using assembly, using the code in the textbook, it won't work for your KCP SM6, which is the one we are using. It's the most, the latest version of it, which is this one. There's an official user guide, and don't spend too much time on it. So try to follow the tutorial first, because I already gave you the answers for when you are doing the tutorial. You'll get a chance to practice with some not really given problems in the lab. We have a lab for this one as well. So don't spend too much time on reading this. You will get distracted a lot. It's boring to read it. It's better to just directly get into it, get your hands on it, and duplicate whatever I have in the tutorial, and upload it, and see something happening on the board. Start from there. Okay. So this is KCP SM6. Keep in mind, it's the latest version of it. And don't use this one. Okay. If you find a core called KCP SM3, it's a wrong core to use. Don't use that one. Use the KCP CM SM6 instead. Right. And these are snapshots from the textbook PDF version of it. So let's take a look at the. So that's instruction memory. So the instructions will be saved here, and I might be wrong saying it's 8-bit, so it's not actually. So look at the instruction width. It's actually 18-bit. So this one, each row here is 18-bit in the instruction memory.
Mm-hmm.
The registers are still 8-bit, so if you count it, it's like 8 plus 8. So I think it's just for the instruction itself, not for the data. See, the data has the data memory as well. So 00 means it's a hex number, right? So it's actually 8-bit in there. These are the registers names. Keep in mind, that's why sometimes you get confused where do I get an S for hex? It's not hex, it's just the name of the register. Okay, so the S0 is a register's name. If you compile it, it's going to be converted into the address of the register. So the address of the register will be 8-bit, I guess. Yeah, 8-bit general purpose registers. There are 16 of them, including S0 to SF. Okay, 16 of them you can use. And 64-byte data memory, it's tiny compared to the like several gigabytes RAM. This is like 60-year-old CPU probably. 64-byte data memory, all right, it's here. And 10-bit instruction address, so which means you can have 2 to the 10th number of instructions. So it's a limitation to the length of your assembly code. That makes sense? 10-bit address, right? Which means it has 10 bits to resolve all these rows. There's 2 to the 10th rows in there. It's not the width of the memory of the data of the instruction itself. It's just the number of memory banks in there. So you have up to 1024 instructions you can put in there. But I think we probably are dealing with like 20. I think the project is a few hundred, way lower than 1024, so it's good enough for us. And if you look at the the architecture of it, you can see, again, you don't have to worry about all the physical connections and why it makes sense. The digital circuit design, I don't even know. I think this is IP for them. They wouldn't disclose it, so nobody knows it, and it's not necessary to understand what's going on for the hardware connections. You have to convert your mind from trying to understand this bottom level circuit from BSI to a one level up. It's Verilog level, RTL level, instead of the bottom transistor level circuit. Okay, so the instructions also have several flags. These are some new things that you have to pay attention to. So it's difficult to explain what's going on for the flags, but if we get into the instructions, you understand what's going on. So for example, this is assembly, right? This is one line of assembly code. Okay, if you haven't programmed the assembly, this is the first assembly code you have. Okay, and space, SX, space, comma, and you can have a space here. You don't have to, but usually they will. It looks better. And SY. This is ending these two 8-bit binary numbers bit by bit. That's why it's called bitwise operation. So see what's actually going on is this and this bit by bit, and the result is being sent back to where? SX. Okay, so XX will be changed. So if you want to use SX for some operation, you have to save it somewhere else first, right? You don't want to lose the data. Unless you don't need it anymore in the future. Okay?
What if we need X before, again, on a different operation?
Yeah, so I have to save it somewhere else. Yeah, there must be a store. Usually it's called, what's assigning? It goes in instructions, right? So there's assignment, I think. Usually it's called load. Yeah, load. Okay, see, SY assigned to SX. The instruction is load. How many registers you have available? 16. So I have a lot of empty ones you can use.
Okay.
You can use one of them as an intermediate register. You load it here to save it temporarily and then do some operation and come back to use it again, right? Okay, and now let's come back to the AND operation. So the AND operation will do this and send a 0 to carry. why do we need a carry? We don't need a carry here, but it's just something maybe useful for some of the instructions, but I don't have example here, but in the future you'll find out. So what is a carry? Let's look at here. It's a flag. Sometimes it's useful just adding more functionality to it. Sometimes you need a flag to as a sign, do something. When you program it, you'll find out later, okay? Now let's move to the second one. So these are registers, like memory banks or different flops, so they can store data in it, right? But also you can do an AND operation with a constant. I think KK is a constant. So it's not a register anymore. It's a number. Okay, so you can do that as well. Make sense? So the compiler actually can understand it. It's just doing actually whatever in the register or whatever the constant is, it's just to do the AND operation, right? Same thing. Bitwise operation and put it in SX and give a 0-2 carry. So carry is not always being used or being updated in all the instructions, but it does it here for some reason. We'll figure out later. Or similar, XOR similar. It makes sense, right? There's no carry for AND or XOR.
Yeah.
Whenever you gotta add, right? So this add doesn't have a carry flag. Keep in mind, if you don't need a carry flag and you know there won't be any overflow, it won't exceed the 8-bit range, right? It's half adder. No, half adder even have a carry out. But anyway, so this is just adding a addition operation without carry out anything. Okay, very simple addition. It's just adding these two registers numbers and put it in SX. Add a constant. This one has a carry. All right, add with a carry flag. This is like getting a carry in or something, right? So the carry is just a universal carry. It's not a carry belongs to anything. So if the carry has been asserted or being set, or you put a 1 in carry somewhere else by other instructions, and followed by this instruction, then carry won't be 0 anymore. Keep in mind, you have to clear the carry if you know something. So for assembly programming, you got to know what you're doing, right? If you don't know what you're doing and you use the add cy and you don't know what is C in there right now, you got screwed. So you have to look into the programs before this and know exactly the result for each instruction in order to make it right. So it's very difficult to debug. Imagine you have thousands of lines of assembly and got like 100 bugs in there. It's difficult. Yeah, that's why engineers are getting better pay, because they are taking a lot of challenges other people couldn't take. Same, adding a constant, but carry is being added to it as well. It isn't showing here, but you should know that it's doing it for you, right? Subtraction. Subtraction with a carry. Subtraction with the carry. It's just adding more functionalities. It's not required. It's not saying like you have to use this instruction to do it. Whenever you have a carry, have a flag, it's just more flexible. You are thinking, hey, this thing got a carry. I probably can use that carry as a signal for my other programs, because you don't have like if statement in here. You know, if something is what, then I do something, right? You got a signal, it's kind of like if. You know what I mean? And then you embed that programming technique, not in English, but in hardware computation or binary computation. You know, it's not saying you have to minus carry here because of the math. It's like I want to use a carry to here so I can reach my goal. You know what I mean? Since you don't have loops, you have loops, but you don't have, because the loops will, it's like a jump in assembly. You can jump to somewhere, and then whenever that calculation is done, you can jump back. But like for loops, if statements, these kind of things, you just don't have it. Compare. So this, I think this is the old instruction, but this is a new one you want to use. And you can see that by compare the numbers in these two registers, you got a 0. So Z, if you look at the flags, you have how many flags you have? It's, so again, so the flags, zeros, carries, they're just adding more capability to the programming because you don't have statements and for loops, right? And switch, don't think about switch and case. Pointers, no. Okay, let's see compare. It's a very interesting instruction. It compares the two registers, and if this equals this, then you got a 1. So this is kind of something you can implement a very similar operation with the if statement, right? How to do it? Think about it. How to do it here, assembly. So compare these two registers. So in if statement, you do like if they are equal, or if this is larger than this, then I do what? Do the next, right? But here, compare. You compare, then what's next? It's changing the values of Z and C. See? See, if they are equal, you got a 1 in Z. If this is larger than this, you got a C as 1. Otherwise, C is 0. So it covers all the situations. Equal, larger, less, or smaller, right? So we got a Z and C's is going to hold a different value in there. So what's the next? For example, I want to do something like if they are equal, then I'm going to do something, right? In assembly, which I'm going to do with a compare instruction. If they are equal, then I'm going to do something, right? I do a compare first. Now I know Z is running behind the scene. The value of Z will be changed. Okay. If they are equal means if Z becomes 1, then I'm going to do something. Again, you don't have an if to judge if Z is 1.
Okay.
How to do that? So if Z is a 1, you can minus Z from 1 or AND Z with a 0, do an AND operation with Z, right? So Z can be 1, can be 0, okay? If Z is a 0 and you AND Z with 1, you're getting a 0. If Z is 1, you AND whatever, it's gonna still be that thing, right? You can do an AND operation afterwards, and then there's another instruction like you can make a judgment if if it is a 0 or not, to jump to somewhere else to do other operations. Okay, that's one strategy to implement if statement. So what about test? Very similar. So test is not looking into like if they're equal or larger and smaller. It's just doing a AND operation, like what I said, right? After compare, you can add AND Z with something. right? If you're getting zeros, then it's probably not a good example, I think. I don't have a really full example for you guys. But the idea is you have all these instructions try to implement whatever you don't have in assembly, like if, for, switch, right? So what's this one doing here for you guys? So test, right? So it's ending these two registers, and then you can see if T is 0 or not. If T is 0, which means one of them is 0, okay? Then Z becomes 1 or 0. Otherwise, oh no, if T is 0, then do this, else do this. But C, no matter T is 0 or not, C will be, what are these ones?
What is T?
Oh, it's oh, T is because you know, so definitely if you look at this one, this line, you know T is not 1 bit, right? Okay, so the test function is going to return a value to a T which is an 8-bit number. But any number in the 8-bit system is 8-bit, never mind. It's going to be 8-bit. But the flag probably are not 8-bit. The flags are 1 bit. I might be wrong, might be right, I don't know. I'll look into that later, but at least I think these are 1 bit. These are just 1 bit, just like a flag being asserted or reset. But what about T? So by here, you'll definitely know that T is 8-bit, right? So the results, this and this, if it's a bitwise AND operation, it makes sense. So all the bits are ANDing to each other, and the final result is being assigned to T, which is another 8-bit number. Okay, so this can be it can be used for in a lot of situations. And then you XOR all the bits in T, then you get a C. So C is definitely 1 bit, right? What is this XOR operation doing? Well, remember what is the XOR? If you XOR all the bits in the byte, what is it doing? We did it in embedded, one of the tutorials before, remember? Even or odd number of ones in there. If you have even number of ones, then what is C? 0, right? Yeah, should be 0. If you have odd number of ones, it should be 1. Okay, so by using the test instruction, you can get a lot of information from the from the results here. This can be some information reflecting what are in XX and XY. Okay, it's not like directly being used for program, but you can use this technology or technique to do something for programming. They're just adding another layer in it, right? They provide this special instruction for you to use. If you're smart enough, you just use it for whatever you have to. You just don't have the if statement and for loops. Again, this is whatever they are provided that you can use. Okay, so another thing you can use. I have to tell you, I haven't used all of these kind of fancy functions in the programming examples, but it can be a very interesting thing to learn. And I could tell you that all the other embedded systems can be ARM, RISC-V, or if you go to the industry, it can be 32-bit CPUs. The assembly programming techniques can be very similar. So whatever you learn here are transferable to a different architecture. So they all have like add, and, jump, load, sometimes called store for the MIPS architecture, like the ones in our desktops. There are different architecture, similar. Yes.
after lunch, do I have to go maybe at 12?
Oh, you have that stroke thing right now too.
Yeah. I'll finish it in like 5 minutes. Okay. Yeah. All right. One more thing. So all the instructions you can read through. If I go through it, you'll forget it in the next second. So it's not making too much sense. So you can see jump, right? So you can jump to different places. Call and return. I have examples for you guys. These are very good examples. Directly copy and paste. So you can learn it really quickly. So one more thing you need to know, all right? It's a very interesting way to program. So you put the assembly code in the text editor, like Vim. You code it up. You just open up Vim from command line. Remember the way we did it? And code it up, like add whatever, the assembly code in there, right? And you'll save it as a file. I think change the extension of the file's name to PSM or something, okay? And then there's a software you can use, like these ones, the KCPSM6.exe and also rom.v. So all these things, you have to put them in the same folder. And then run some script in command line, compile your code, assembly code, into a Verilog. There's no way that you can add a Verilog, you can add assembly into your Vivado, right? It's just synthesizing Verilog only, .v files. So you have to convert your assembly code into a Verilog code, to .v file, by using the software I provided. It's very straightforward. Just follow it, right? I'm just let you know what's going to happen. Put in the same folder, run the script. It's going to compile your assembly code into a .v file, a Verilog file. .v file will have all the machine code in there converted from assembly, and then you can directly use it as a ROM file like you have been using for your top module in Verilog. You're just adding that rom.v, because that rom.v has all the instructions, the 1 zeros in there. That's how that works. It's a big picture of it. And as an example of it, and some of the, these are directly provided, so you can practice with it. So eventually we'll understand what's going on, running through the fundamentals. It's not challenging at all, just let you guys know, because the examples, the code, everything, the video demonstrations are provided. Just do it. And then I will be here to answer any questions you may have. And what's the lab for today? 23rd. So we don't have a lab today, right? So I have a 2-week wait.
That was due over spring break.
Yeah. Oh, so that's the last one, but okay. Yeah, anyway, so either, hey, that's interesting. I put a spring break data here. Sorry for that. I'll change it later, okay? And anyway, just work on the tutorial first. We've got a lot of things to work on. Keep you guys busy, okay?
Yeah.
So I'll be here during the labs time today as well, so we can ask any questions we have.